There are 9 languages you can choose from the audio track. Go to Setting and select your preferred language audio track. Also, I have included the link to download the FreeCAD file in the description. I created a timing belt animation by Assembly 4 previously. Both pulleys are same size and it is easier to create the conditional expression to generate the motion. I included a link in the description and at the end screen if you want to watch it too. I think if it is possible to create the motion if the pulleys are different size. So I give it a try. The challenge is 2 pulleys rotating at different speeds and I need to make a smooth transition when the speed change suddenly. Let me start now. Create a new file. Switch to Assembly 4 Workbench. Create assembly file. Create a new body under the Parts folder. So there will be a default LCS for the body. Just hide the coordinates. Then select the body. And create a new sketch. Go to the Model panel. Select the LCS as the reference. Return to Task panel. Select Plane Face, which is the XY plane. Open the sketch. Draw 2 circles. Change the circles to construction lines. Set the diameter of the big circle as 112.75 mm, which is the outside diameter of the 36-tooth pulley. Give it a name D1. Set the diameter of the small circle in term of the big circle. Select Sketch Pulley LSK, Constraints. Type D1. -2 by 3.2. There is error message because the unit doesn't match. Type mm as the unit and it is fine. So the distance between 2 circles is 3.2 mm. Return to normal drawing mode. Draw centered arcs. Switch to construction geometry. Use poly line to draw 2 lines. Trim the middle portion of the arc. Set the angle of the construction line as 155 degrees. Return to drawing mode. Draw 2 lines to join the arcs. Make the lines parallel to the construction lines. Use poly line to join 2 arcs at the top. Make these 2 lines vertical. Create fillet at these corners. Snap this point to the construction line. Snap this point to the construction line too. Snap this point to the arc. Set horizontal distance as 3.4 mm. Make these 2 points symmetric to the y-axis. Now define the radius of the fillets. Set this one as 0.8 mm. The radius at the bottom as 0.6 mm. Make these 2 fillets same radius. These 2 are the same. Leave the top dimensions not defined for now. Close the sketch. Select the body. Make a duplicate. Move the new body to the Parts folder. Rename it as Pulley S. Hide the body Pulley S. Return to the sketch Pulley L. Define the distance as 12 mm. Vertical distance as 2 mm. The sketch is fully constrained. Close the sketch. Create a new sketch under Pulley L. Go to Model panel. Select LCS as reference. Return to Task panel. Select Plane Face. Open the sketch. Draw a circle. Diameter is pulley L, SK, constraints, D1. Draw another circle. Diameter 30 mm. Close the sketch. Switch to Part Design. Extrude a body. Select pulley L as the active body. Symmetric to plane. Length 20 mm. Select the sketch pulley L, SK. Cut the space. 20 mm. Symmetric to plane. Or use the type through all. Select the pocket. Apply polar array. Change occurrences to 36. A pulley with 36 teeth is created. Pitch 10 mm. Hide the pulley L by pressing the space bar. Open the sketch pulley S, SK. The outside diameter of the small pulley is 55.45 mm. Click the diameter of the big circle. Click the expression engine icon. Enter 55.45. The dimension of the smaller circle also change by the formula entered in the sketch. Now define the vertical line as 2 mm. And set the horizontal line as 12 mm. The drawing is fully constrained. Make pulley S active. Create a new sketch. Select XY plane. Draw a circle with diameter 55.45 mm. It is the outside diameter of the 18-teeth pulley S. Draw another circle. Diameter 15 mm. Extrude. Symmetric to plane. Length 20 mm. Select the sketch pulley S, SK. Cut the space. Type through all. Symmetric to plane. Select the pocket. Apply polar array. Change occurrences to 18. A 18-teeth pulley with 10 mm pitch is created. Hide the pulley S. Switch back to Assembly 4. Because I want a default LCS for the body created. Create a new body belt. Create a new sketch. Same as usual, go to Model panel to select the LCS. Return to Task panel and select Plane Face. Open the sketch. Draw a stadium from the origin. Set the diameter of the top circle as 114.34 mm. Center to center distance as 162.509 mm. Delete the constraint number 5. This is the constraint keeping top and bottom circle equal. Now I can change the size of the bottom circle. Set the diameter as 56.1058 mm. Drawing is fully constrained. Box select the drawing. Apply Offset tool. Hit the J key to add offset constraint. Enter 1.676 mm, that is the thickness of the timing belt base. Close the sketch. Switch to part design. Extrude. Select belt as the active body. Symmetric to plane. Length 20 mm. Hide the body belt. Switch to Assembly 4 workbench. Create a new body called tooth. Select the tooth. Create a new sketch under the body tooth. Same as before, go to Model panel and select LCS. Return to Task panel. Select Plane Face. Open the sketch. Use poly line to draw the shade. Make this line horizontal. Select these 2 points in the y-axis. Use Symmetric tool. Select these 2 points. Set vertical distance as 0.2 mm. Select these 2 points. Set vertical distance as 1 mm. Select these 2 points. Set vertical distance as 3.5 mm. Select these 2 points in the y-axis. Use Symmetric tool. Also select these 2 points in the y-axis. Use Symmetric tool. Create fillet at these 4 corners. Set this line as 7 mm. Set radius as 0.2 mm. This one is 0.8 mm. Make these 2 arcs equal. These 2 arcs are equal to. These 2 points are 3.5 mm apart. Make this line 20 degrees from the y-axis. The drawing is fully constrained. Close the sketch. Make the body tooth active. Select the sketch and extrude. Length 20 mm. Symmetric to plane. Hide the coordinates. Hide the body tooth. Go to the assembly. Switch to Assembly 4. Create a new sketch called Master. Go to Model panel. Select LCS as reference. Return to Task panel and select Plane Face. Open the sketch. Create the path for the motion first. The teeth are not attached to the path. It is only for reference and for attaching the pulleys to this path. Diameter of the top circle is 114.592 mm, which is the pitch circle of the large pulley. Diameter of the bottom circle is 57.2958 mm, which is the pitch circle of the small pulley. Center to center distance is 162.509 mm. Total length of the belt is 600 mm. And the pitch is 10 mm. Draw a stadium. Set the diameter for the top circle as 114.592 mm. Set the center to center distance as 162.509 mm. Delete the constraint number 5, which is the constraint between the top and bottom circles. Set the diameter of the bottom circle as 27.2958 mm. Close the sketch. Select the LCS origin. Duplicate. Move the LCS into the assembly. Rename it as UC for upper center. Duplicate the LCS again. Rename it as LC for lower center. Move it into the assembly. At LC, change Y to minus 162.509 mm so it moves to the center of the bottom circle. Add variable. Enter angle as the name. Value is 0. Create another variable, radius. It is for the top circle, 57.29 mm. Hide the assembly. Show the pulley L. Select the pulley L. Create new coordinate system. Select the circle. Click concentric. Change Z to minus 10 mm to put the LCS at the center. Hide the pulley L. Show pulley S. Create new coordinate system. Select the circle. Click concentric. Change Z to -10 mm to put the LCS at the center. Hide the pulley S. For the belt and tooth, I will use the default LCS. Show the assembly. Insert part. Insert the tooth. Select parent system. Select LC origin from both sides, and click OK. The tooth is now attached to the origin. Select the tooth just imported. Create expression array. X array is created and the count of the element is 1. Under the expression array, the XY position is the location of the element reference to the origin. So I can change the XY value to move the element. When there are more than one element, an index is assigned to each element. I is in capital letter for index. 0 for the first element. 1 for the second element, and so on. I set up a variable angle to change the XY position. For example, the expression for X position is variables.angle minus index times 10. When angle equals 10, X for the first element is 10 minus 0 times 10. It is 10. Then the X value of the second element is 10 minus 1 times 10. It is 0. So the X value for the third element will be minus 10, and so on. I divide the path into 4 sections. Angle is used as variable and it refers to an angle within the circular path. But it refers to the linear distance within the straight path. In fact, you can treat it as the linear distance along the whole path. For the top circle, the angle sustained by the belt is 200.3 degrees. The linear distance is also 200.3 millimeters. But it is easier to explain it in terms of angle for the circular path section. From point A to point B, the angle is minus 10.15 degrees to 190.15 degrees. From point B to point C, at the distance 159.96 millimeters to 190.15. So C is 350.11. From C to D, because the speed of pulley S is double of the speed of pulley L, the angle used for this range is 159.693 divided by 2 equals 79.85 degrees. In fact, the linear distance of this section is 79.85 millimeters. Add 79.85 to 350.11, so D is 429.96. From point D to point A, add 159.96 millimeters to 429.96 is equal to 589.92. From point A to point B, when the angle is smaller than 190.15 degrees, X position is radius times cosine, variable. Y position is radius times sine, variable. When the variable is greater than 190.15 degrees, X position is calculated from the horizontal component of the distance from point B to point C. Subtract 190.15 from the variable and use it as the hypotenuse of the right angle triangle. Use letter L as the hypotenuse. So the horizontal component is L times sine, 10.15 degrees. X position of point B is minus radius times cosine, 10.15 degrees. So x position along this straight path is minus radius times cosine, 10.15 degrees, plus L times sine, 10.15 degrees. For y position from point B to point C, it is based on the vertical component of the distance moving from point B to point C. Similar to the calculation for x. Y position along this straight path is minus radius times sine, 10.15 degrees, minus L times cosine, 10.15 degrees. The variable is variables.angle minus index times 10 because the pitch is 10 millimeters. Radius is 57.2958 millimeters and is represented by variables.radius. Substitute with the actual variables used in assembly 4, I get the expression in red. For conditional expression, the format is condition, question mark, result true, colon, result false. We put the condition before the question mark. If it is true, run the expression. If it is false, run the expression after the colon mark. The condition for this section is variables.angle minus index times 10 is greater than 190.15. Using the conditional expression format, I combine the expressions to form the conditional expression highlighted in yellow. Change the count to 2. For this example, the expression may not work when I increase the count for the section of the small pulley. It is because the speed is double. So I use 2 elements for testing to make sure it works. Copy and paste the expressions to x and y. Run the animation. Select angle from the variables. Begin from minus 10.15. End at 350.11. Step size 2. The expressions are correct and 2 elements move along the path. For section C to D, the rotation speed is double because the diameter of the small pulley is half of the big pulley. Then the variable will jump from 350.11 to 700.22 suddenly at point C. For calculating the x and y position, the angle starts from minus 169.85 degrees. So the variable for this section is variable minus 700.22, minus 169.85. The variable used in assembly 4 is variable.angle times 2 minus index times 20 minus 870.07. Therefore, x position in the section C to D is cosine, variable, times the radius of the small pulley. Then I come up with the expression indicated by the red arrow. For the y position, the vertical component is sine, variable, times the radius of the small pulley. As the variable is double suddenly at the point 350.11, I need to adjust the position for smooth transition. Y position of C is minus 167.55 in the section B to C. And Y position of C is minus 5.05 in section C to D. So the difference is minus 162.5. Include minus 162.5 in the expression. The final expression is as indicated by the red arrow. Let me review the conditional expression again. This is the format of conditional expression. When there is subconditional expression, just replace the result false with the subconditional expression. You can add as many as you need. Just make sure you add corresponding open and close brackets as indicated by the red arrow to separate the subconditional expression. Go back to the expression for section C to D. When the variable is greater than 350.11, these are the expressions for x and y positions. Combine with the conditional expression from A to C, I come up the conditional expression from A to D using the format with subconditional expression. For section D to A, the x position is the horizontal component of the distance traveling from point D to point A. So it is sine 10.15 degrees times variable. Initial value of x of point D at 429.96 is 28.20. Therefore, the expression is 28.20 plus sine 10.15 times variable. For y position, it is the vertical component of the distance traveling from point D to point A. So it is cosine 10.15 degrees times variable. Initial value of y at D is minus 167.55. Then, the expression is minus 167.55 plus cosine 10.15 times variable. With the condition variable is greater than 429.96, I come up with the expression for x and y in section D to A. Combine with the previous expression for A to C, I got the complete conditional expression for the whole path as this. Copy and paste it to position X and position Y in the placer. Change the range to 589.92. Run the animation. It looks good. Change count to 60. The range is from minus 10.15 to 589.92. Run the animation. But the teeth didn't follow the path. Change the range begin from 579.92. Run the animation. Now all teeth move only 10 mm along the path to generate the animation, and it is good. However, the orientation of the teeth is not correct. To correct the orientation, turn the tooth by 90 degrees anticlockwise first. And keep changing the angle as the variable. When it reaches point B, the angle is constant, which is 100.15 degrees. For section C to D, keep changing the angle as the variable. However, the rotation speed is double, I need to adjust the value at point C. So it is same for both section B to C, and the section C to D. The angle at C is 100.15 degrees. Reset the value at C to 0 by deducting 2 times 350.11, and then add 100.15. Therefore, the angle for section C to D is 100.15 plus 2 times variable minus 700.22. After point D, the angle is constant, 259.85 degrees calculated by the formula above. Put these expressions in an Excel file. Add the conditions before the expressions and combine them as one conditional expression. Copy and paste to the angle field of the expression array. Run the animation. The angle is correct now. Insert part. Insert the pulley L. Select parent assembly. Match UC to LLCS. Insert part. Insert pulley S. Select parent assembly. Match LC to SLCS. Go to LLCS of pulley L. Go to Angle field. Type minus variables and select angle. Go to SLCS of pulley S. Go to Angle field. Type minus variables and select angle, times 2. The small pulley and the teeth do not match. Rotate the pulley by 1 gear should fix the problem. Go to pulley S. Go to the Angle field. Change the angle to 10 to rotate the pulley. The pulley and the teeth match now. Insert part. Insert belt. Select parent assembly. Match LCS origin from both sides. Run the animation and it is fine. Select the tooth and right-click to get the manual. Select Appearance. Change the line color to light gray. Same for the belt. Change both pulleys to amber color. Run the animation and it is fine. Hide all the LCS and master sketch. As there are many elements, the speed is slow. I can export it to MP4 video to run it faster. Click Save. Select the folder and give it a file name. Change width to 1920, height to 1080. Adjust FPS to 30. Use 50 for the number of loop. Click Create and Save. Close the window. Run the MP4 video. You can change the step size in the animation to change the speed too. Please subscribe and give it a like. Thank you for watching.